Hi guys, these are going to be the notes for types of energy. These should match your printed notes. If you want to follow along, the example problems will be the same as what you can see in the PDF. So in the past, in science, you've learned about a lot of kinds of energy, things like thermal energy, nuclear, chemical, all kinds of different energies. For our purposes, we're going to focus on something called mechanical energy. Okay, so that's different than chemical energy or thermal energy or any of those others. Mechanical energy is a category, and it talks about the energy that an object has because of where it is, so that's the position part, or because it's moving in some way. Okay, so we'll have three total types of energy that we're going to look at. One is kinetic energy, okay? And then we have two different kinds of potential energy. Potential energy includes elastic potential energy and gravitational potential energy. First, we're going to focus on potential energy. So potential energy has to do with where the object is, and we're going to break it down into two different types. So we've got gravitational potential energy, which has a whole lot to do with height, and elastic potential energy, which has a whole lot to do with whether the object has been stretched or compressed in some way. GPE, or gravitational potential energy, is what we're going to see the most often. All types of energy are going to be measured in joules, just like work was. And we have a formula for gravitational potential energy, which is mass times the acceleration due to gravity, 9.8 meters per second squared on the Earth, times the height of the object. So this height part is the clue for what GPE is all about. The more height an object has, the further off the ground it is, the more GPE it's going to have. Okay, so let's say that you're in a roller coaster and you're up at the very top of the highest hill. You have a whole lot of GPE simply because you have a really, really tall height relative to the ground. Okay, in this example problem, we want to find out how much GPE the roller coaster has if it has a total mass of 735 kilograms. And it's at a height of 139 meters. And then we're going to assume that it's on the Earth, so G is 9.8 meters per second squared. So our formula for GPE is M times G times H. So we're going to do 735 kilograms times 139 meters times 9.8. I'm sorry, I just realized I drew those out of order of what the formula actually says. You're multiplying them all together, so ultimately it doesn't really matter what your order is. Okay, so when I multiply all that together, I have 735 times 9.8 times 139. I get a GPE of 1,217 joules. You can shorten that if you'd like to 1 times 10 to the 6th joules. Okay, our second question is, where did that energy come from? Well, the roller coaster had to do, or the chain or the engine did a lot of work to get that coaster to the top. And so the GPE didn't come out of nowhere. It came from the work that the engine did to get the coaster to the top of the hill. Our second type of potential energy we want to look at is called elastic potential energy. So with elastic potential energy, we still consider it to be stored, but the reason it's stored is that you stretched or compressed something. So when you stretch a rubber band, it wants to return to its normal length. When you squash a little pop-up toy down, the spring, again, it wants to return to its normal length, and so that would be considered stored energy. We can calculate elastic potential energy. To calculate it, we're going to use this formula. So K is called the spring constant, and that usually is going to be a given number. They're just going to tell you the spring constant of the spring or the rubber band is blah, 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 some number. Okay, and then X can be either the compression distance or the stretch distance. And again, that's something the problem will tell you. It might say the bowstring was stretched to a certain length in meters. That's going to be your X. Notice that X is squared in the formula. That's an important thing to remember when you're putting in your calculator. So for example problem, we have an arrow with a mass of 0.25 kilograms. It's pulled back in against a bow, a distance of 0.6 meters, and so that's going to be that stretch distance. That's our X. Because the arrow is pulled back to that distance, it has elastic potential energy because it wants to fly forward, right? As soon as the person lets go, it's going to move. The spring constant is K. That's given as 415 newtons over meters. And we want to know how much EPE does the arrow gain as it's pulled back. So our formula for EPE is 1/2 times K times X squared. So we're going to plug in the K of 415, and we're going to plug in the X of 0.6. We want to square that X. Notice that the mass is actually not included here. As always in your calculator, I would recommend that you do 0.6 squared first, especially if you're not so good at parentheses. So it gives me 0.36, and I'm going to multiply that by 415, and multiply that by 0.5, and I end up with an EPE of 74.7 joules. If we are rounding for good sig figs, that's going to be 75 joules. Where does that energy come from? Well, the person pulling back the bow had to do work, right? And so as he or she pulled with a force back for a certain distance, aka X, work was done. And that equals the EPE that the arrow now has. Our last type of energy is called kinetic energy, and that does not depend on where it is, but rather what it's doing. So if you look at the formula here, KE equals 1/2 times mass times velocity squared. The velocity is super important. If V is 0, then there is no KE, right? If the object's not moving, then it does not have kinetic energy. The second important thing to notice here is that V is squared. Okay, so it's important to put that in your calculator, but it's also important if you think back to our momentum stuff that we did last week. We talked a lot about car accidents and collisions, and we talked about how the damage done is exponentially larger if your speed increases. So like you double your speed, you actually quadruple the amount of energy change, and ultimately that corresponds to damage done. So more speed equals a whole lot more energy, and that's because of the V squared part, right? So if V is 2 times, that's 2 squared. Or if you've tripled your speed, that's 9 times more energy. So if you're going 3 times the speed limit and you crash your car, you've just done damage to the amount of 9 times more change in energy. That's going to be a significant change in energy. So, moral of the story is don't drive fast. Okay, for our example problem, boy can kick a 0.5 kilogram soccer ball, so they gave us a mass. At about 20 meters per second, we would like to find out the kinetic energy the ball has. So our formula is KE equals 1/2 mv squared. We're going to do 1/2 times 0.5 kilograms times 20, and we want to square the 20. And just like with EPE, start at the back end, so do 20 squared first, and that gives you 400, times 0.5 for the mass, times 0.5 again for the 1/2, and you end up with a KE of 100 joules. Where did the energy come from? It came from the boy who kicked it. So when he kicked it, he pushed, he had an applied force, right? The ball moved a certain distance, and so what do we call that? We call that work. The boy did work. The ball now has energy.